team. So I don't have any other announcements or needs, but Brandon, time's yours, and we look forward to asking you some questions afterwards.
Okay, thank you. I appreciate it. Oops. Well, I'm Brandon Schmidt. I'm the HPC System Support Specialist at UNI, and I'm here today to talk to you about the HPC. So an overview of what I'd like to cover today. First, I heard some of you guys might not even be exactly familiar with what the HPC is. So I'll briefly go over what the HPC is and what it has to offer. And then we'll talk about how you can use the HPC and get the most out of the resources that we have available. And then next, we'll talk about how to access and actually use the HPC, because obviously you have to do it remotely. So it'll be something nice to walk through. And then we'll go over some of the things briefly that the HPC is being used for, and then I have a little demo that we can go through. So starting off, what is the HPC? The HPC is a group of compute nodes that work together to solve problems that are too large or memory intensive for regular computers to handle. And you can see a photo of the HPC right here. Now, obviously the HPC is just a bunch of regular computers. They're high performance CPUs and large amounts of RAM, but all of these work together. We have a bunch of compute nodes, and we have a head node, and we have a node that you log into, and all these work together to solve problems. There's no user interface, so we have to connect remotely using command line. We can accept job requests and then put them into the queue, and that's how you submit and get things done. Job processing time isn't an issue because the HPC is running 24/7. This is an important thing because if you were running on your local machine, you'd be using all the resources that you have available, and you can't do anything else until you're done. And that could take days or weeks using just a regular computer. So what are the advantages of the HPC? Memory intensive tasks become possible. Obviously on a regular desktop, you might be lucky to have 32 gigabytes of RAM. On the HPC, each node has 128. So if you need 60 gigabytes of data to be loaded in and worked with, then we're able to do that. You can run for long periods of time. I mean, most jobs on the HPC run for, I'd say like 8 hours, but sometimes they run even longer than a day. And on a desktop, that would take a serious amount of time. We have a large number of CPUs available for parallelization. We'll get a little bit more into parallelization because that kind of is the main way you want to use the HPC. It's not the only way, but it helps a lot, and that's what speeds up the process. Its advantage is simple. It just has more resources than a regular desktop. But the tricky part with using the HPC is trying to get all of the value out of these resources. Okay. So what the HPC isn't is it's not a black box that'll magically make things run faster. So if you have code and you're running it on your desktop, you can't just move that to the HPC and have it run much faster. You have to put some thought into making sure that you use all of the resources on the HPC and actually get value out of it. It's not a place to test and develop code. If you want to run a project on the HPC, it's easier to develop the code and then put it on the HPC, and you want to test it on your local machine. That's a lot easier because working with command line on the HPC, it's doable, but it's not great for you, and it's not great for the resources on the HPC. It's not a free storage space. When you're done working with HPC, you need to clean up your home directory. Last semester, we had a student that took up all available storage space on the HPC, and we weren't able to run anything until he was able to clear out his home directory. So it's important that you don't just leave things stored on there. So I have some details about the HPC. We can see that for the storage, we have 60 terabytes. So that's kind of a lot, but when you split it among a lot of people and each person is using large data sets, it can go away pretty quickly. The RAM, actually, I was wrong. It's 512 gigabytes, so that's significantly more. And you can work with large data sets. We have some AMD EPYC cores, which each of these CPUs 32 cores. So that's a lot of resources available because most desktops are just 8 cores. And you can see we've made some new additions in 2024, new compute cores and new GPUs. Okay, so parallelization was how we get more out of what we have. So parallelization is the process of splitting into separate tasks and running those tasks at the same time on different threads. This can only be incorporated when the tasks are independent. So I have 2 diagrams here, one of sequential tasks, right? So task 1 runs, task 2 runs, task 3 runs, and you have to wait until each task is done before we can start the next task. But when we run tasks in parallel, we'll start, say, the first task, and then we'll run two on one node on one CPU, task three on one CPU, task four on one CPU, and then when all those are done, we move on to task five. So you can see that if all these tasks take, I don't know, 1 day to complete or 1 minute to complete, this will take 5 blocks of time. This will only take three because all three of these are running at once. Yeah. When a job has many independent tasks, this is when parallelization can save a huge amount of time. Because we saw that the CPUs on the HPC have a lot of cores. So when we're able to use all these cores and run things in parallel, we can save a lot of time. An example I have is baking a cake versus making a burger. We need to think also about what we're trying to do. Because if, for example, we're baking a cake, we can't exactly do that in parallel and we can't save time using the HPC. Because first you got to get the ingredients, that'd be task one. Mix it together is task two, bake it task three, put frosting on it as task four, and then put candles on it as task five, right? You can't put it in the oven and also put frosting on it at the same time. So we can't save time with parallelization. We need to think about what we're doing. But if you're making a burger, for example, first you get the burger order, and then task two could be making the burger, getting some lettuce, getting some onions. All these things can be done at once, so we can save time. We don't need to wait for the burger to be done to cut lettuce. Oh. Okay, and then this is from the tutorial, which I have on the website, but this is just the output file. And we can see what I did here for each of these tasks was I just computed a really large factorial number. And I didn't save the number, I just computed it and saw how much time it took for the HPC to compute it. And when we just run it normally, and this is programmed in Python like how any regular person would program it, it takes 74 seconds to do all this. Because first, when you're done with task one, we start on to task two, task three, and so on. So we have to add up all of these times to run in parallel, or to run in series. But when we run in parallel, we're only limited by the slowest thing. Now, we're running this on 5 separate CPUs, but you can notice that we're not saving 5 times the amount of time. We're only saving half the amount of time. We're running twice as fast because we're limited by how much each of these tasks weigh. If they all took 30 seconds, then it would run 5 times as fast. But because one of these tasks takes a lot longer than the others, we're not quite saving all the time that we possibly could. But that kind of depends on what we're trying to do. So it's not something we can always control. Okay, how to incorporate parallelization. First, you have to look for independent tasks, obviously. Like these tasks can't be interlinked or depend on each other. With your programming language of choice, if you're trying to program something, look up popular multiprocessing libraries and see what you can do to incorporate them in your code. For Python, I've always just used import multiprocessing. It's pretty straightforward. This is one case where you can use it, where you create a pool and just map that pool to a variable of results. But if you're trying to run commercial software, which is usually what the HPC is doing, like no one's programming simulation for materials. The commercial software already has it baked in most of the time. So using the HPC and SEPs, I didn't want it to seem like, oh, I'm just going to keep adding on more and more things you need to do. So I just wanted to be clear, we have 4 steps that we're going to go through with using the HPC. It can feel a little bit overwhelming, but we'll break it down to make it really simple. First, we'll talk about how you get access to the HPC, get an account. We'll talk about how to connect to the HPC. We'll talk about how to upload your files. And then we'll talk about submitting jobs in the queue. So objective 1, we're going to get HPC access. So before you can even log in and use the HPC, you need to make an access request. For us, you can do that through Service Desk, or you can do it on the website. I have a form set up. So you just fill out the information, and we will likely give you an account. We don't really ask a whole lot of information from you, basically who you are and why you want the account. If your specific institution has a cluster, reach out to your IT department and request an account. That's how you would do it. You can also request access to external facilities. Those likely you need to have like a grant and be doing research, because they're not going to give it out to anyone who wants an account for free. So if you're doing research, though, you can get access to some bigger clusters. You'll need a proposal and a good reason to do that, though. Here's a photo of the access request on the website. So you can see we're just requesting your name, what your UNI email is. asking if you're a student or faculty and why you want to use the HPC. Yeah, that's really all we need to know. Okay, objective 2, how we're going to connect to the HPC. Unfortunately, interacting with HPC, you have to open up the terminal. And I know that seems a little bit intimidating, but it's actually not that bad because there's only really 2 commands you need to know. The first command we'll cover here is SSH. So you'll do SSH, you'll put your cat ID, and then you'll follow it up with @login.hpc.uni.edu. It would be different for someone else's cluster, whatever their @ would be, but this is for us, for example. If you're off campus, you will need a VPN to connect. That is a little unfortunate, but getting the VPN access doesn't take too long. You just request and then you install the VPN. In the terminal, after you've typed the SSH command and submitted it, you'll have to enter your password. It won't appear on the screen though, so just be wary of that. And then you've successfully connected, and that's all you have to do. And I have that here. This is exactly what it looks like. I just submit the command with my cat ID, and I follow it up with @login.hpc.uni.edu. I type my password. It'll tell me some log information like the date and my IP address. And then from there, I can submit commands on the HPC. How to upload your files to the HPC, that's objective 3. So you'll need to not be connected to the HPC. So don't be here trying to run the SCP command. You'll have to be, before you connect, you'll have to run the file transfer command. So open up the new terminal window. You don't want to be connected to the HPC. And then you'll do the command SCP, and then space, and then the path to the file or files that you want to upload, space, the same cat ID @login.uni.edu. And then you'll follow that up with :/home, and then / your cat ID. And that's just your home directory to make sure it goes where it needs to go. So then you'll be prompted for your password, but after you submit your password, it should upload and you'll see the file transfer. And if you can't find the path to your file or it feels a little bit confusing, at least in Windows, you can just right-click the file that you want and then click copy as path, and that's what you can use in the command. And so here I have an example test.txt, and I copied the path. So I did SCP, and then I just pasted the path as text. And I followed it up with my login, and then :/home / my home directory. I typed in my password and then transferred and it uploads. It could take a while if you're doing a large data transfer, but for me, I just had a text file that had like 1 word in it or something. So it ran in 0 seconds. Okay, the 4th objective is unfortunately the most difficult one to understand, and that's job scripts. Job scripts, I feel like, are the most complicated part of using the HPC, but luckily, once you have the job script written, you don't have to write it again. And modifying a job script to fit a new job is fairly easy. So what is the purpose of the job script? So the job script submits the job to the HPC, and it puts it in the queue, and it makes sure that it knows what resources you need to run the job. Once your job script is written, you can submit it into the queue with the command sbatch, and I have that up here. So in my example, I have sbatch connect4.script, and it's submitted. And then when I use sq, you can see it running in the queue. I'm the one who's running it and how long it's been running. So here's an example job script that we're briefly going to go through. So we start off with the hashtag !bin/bash. Every job script should start with that. And then you'll see we followed up with sbatch, all caps with the hashtag in front. And this is what we specify for the job. So sbatch with the job name and then space, and I just put HPC example. And when you see it running on, oh, sorry, the job scripts are different. But when you see the name connect4 here, this would say HPC-example because that's the job name. How many nodes we want to use? For this case, we use 1, and you will almost always use 1. Getting this to be more than 1 is difficult, and you need to put in a serious amount of thought. And then the number of tasks is just how many programs you're running. For this example, it's just 1, even though I am running in parallel. But I'm running in parallel using 6 CPUs per task because all of the CPUs that I'm requesting are all within the same program file. And then for -t, we just specify the maximum job allocation time. This one is set to 10 minutes because I know it's supposed to run in about 2 minutes at the most. So just give yourself a healthy window and then set a cap there. Usually what I see is a 24-hour job time. SBatch no requeue. This basically means if it fails or if it doesn't get done in time, you don't requeue it, it just drops. You don't need the output or the error files, but when you specify this, it gives it a name. Otherwise, if you don't have these two lines, it'll be -O and then a bunch of random numbers and it'll be confusing. So if you have these two lines, you'll know exactly what the output and the error files are called. So in this case, we're running a Python file called tutorial.py, right? But before we run it, we need to module load Python 3.11. We load Python and then we do srun Python and then we specify the file. And this will get it running, or it'll submit it to the queue and then it'll start running. Okay, additional information. You now know how to use the HPC, but there's some other things that are still handy to know when working with it. Unix commands. This is for Linux, any terminal commands. I have a list on the website here, but this is not a complete it's not a complete command list. You can find a complete command list, but what I have here is pretty much anything you'll ever use. I mean, it's more than what I've always used. And I don't see a world where you'll need some obscure commands, but maybe you will, and you can look that up fairly easily. Text editors, for here, I have examples of Nano and Emacs, and these are just editors that'll let you edit the program file in case you need to make some tweaks while on the HPC. Each text editor is different and has different commands, and it helps to find one you like. I don't think it matters too much, but it can help. I think Nano is probably what I'd recommend to anyone. It's fairly simple, and Emacs came out in like the 70s, so it's pushing like 50 years old now. But you can use whatever you want. And honestly, it's just a text editor, so it's not that big of a deal, but pick one you like. Bash scripts, these can be helpful, especially when clearing out, if you have a bunch of directories in your home folder and you need to clear out a specific file. A bash script would be great for that because basically it groups a bunch of commands into a single file, and then whenever you run the file, you run all those commands at once. So if I have a command that's like, hey, go into this folder, go find this file and delete it, and then pop out and do that to the next folder, that's a great way to do that with bash scripts rather than typing in all the commands yourself every time. And then I have a link to the website, which briefly goes over bash scripts too. Optional software. So we talked about doing it through the terminal. You don't have to necessarily do that. You can also use PuTTY for remote connection. This allows you to connect and send the commands to the HPC. It is fine. I don't use PuTTY because, as you can see right here, this is PuTTY, and it looks basically the exact same as the terminal. So it doesn't really change anything, and honestly, it just adds an extra step of, installing some software, which you can just do through the terminal. You can do it though, and some people like it, and it does look nicer, so maybe that'll work for you. The one that is really useful, I think, is WinSCP. This is remote file management, so you can see here, once you connect to the HPC, you actually get a visual interface for the files. So you can drag and drop files, and that makes things a lot easier rather than typing in the command and copying the path. That's a little bit annoying. I still do that because I'm not allowed to install software on my work computer, but WinSCP is a lot easier to use. So that I would recommend. If you're on Mac, though, unfortunately, neither of these work with Mac, but Mac does have its own alternatives that you can look up and use if you'd like. So what is the HPC being used for right now? UNI's physics department has been the largest user of the HPC so far. This is actually where I got my experience using the HPC. I did physics research for 2 years with Dr. Lukashev. They're doing research on a type of materials known as Helsler alloys. They study these materials by compressing the material and then expanding it, and then they run a calculation to see how it affects their properties. The thing is like they'll adjust the input files very slightly, and then they'll run a new calculation. So each calculation will take like 8 hours, which isn't that long, but when you're running tens or hundreds of them, it can get to be a lot. And if the results we get are interesting, then the work will get published. We have some recent publications from last year. You can see I'm on one of them, and there's a lot of students on the other ones. And all of these are Helsler alloys, I think. But yeah, they're all materials science research. Other users, the chemistry department recently brought and installed some of their own software that they'll use to do material science stuff. I'm not a chemistry guy. It does sound interesting, and it sounds kind of similar to what the physics department's doing. The math department is also using it. They're I talked to the guy using it, and he said they're using it to work with high degree polynomial equations. I mean, it sounds interesting. I'm not entirely certain what that means, but uh, the main point is that a lot of fields are able to utilize the HPC for research or educational purposes, and you don't need to be, even if you know how to use the HPC, like you need to apply that to like what you know and what you're researching. It's not currently being used to build neural networks. That's an idea that I think would be great for it. The students have done projects with it, especially in the computer science department, but no one has used it for the HPC yet. But working with large data sets, I think the HPC would be really good with that. Okay, so now we have a demo going through using the HPC. So we're all familiar with the children's game Connect 4. Connect 4 is a game where two players take turns dropping their pieces into 7 columns, and whoever is able to connect 4 wins the game. So now we know how to use the HPC, and we can do all sorts of things with this. And then this demo, we're going to use a minimax algorithm to find the best moves in a game of Connect 4. And so the goal of the game is to create winning threats while also not letting your opponent get too many threats. And I have a link to the website here in case you want to look more into what we did. So how it works, Minimax finds the best move by searching every move that you can make, and then searching every move your opponent can make, and so on. It assumes that you'll play the best move and your opponent will play the best move. So when the algorithm gets to the end and you reach the maximum depth, it'll just do some quick calculations and figure out if it thinks the position's good or not. You can see here, like, this is the starting position, and we have 2 choices here, go to the left or right, and we'll choose the best path for us, and then our opponent will choose the worst path for us, and then so on. The program that runs on the HPC is written in parallel, though. So it'll search all 7 possible moves in Connect 4. As you can see, we have 7 columns, so we have 7 choices where we can drop the piece. And the HPC will search all 7 moves at once, while the program that's written on the local machine will just search each move one at a time. So this is the game of the HPC versus the local machine. This is a game played by 2 computers. The local machine is playing with the red pieces, which is a serious advantage in Connect 4 because if you're playing with the red pieces, you're basically guaranteed to win with perfect play. But the HPC is playing with the yellow pieces, and it's actually able to outpace the one on the local machine. So they're both running the same program and the same algorithm, but the HPC wins because it's written in parallel and it's able to search more positions than the local machine is able to search. So it ends up playing better moves. And that's what I got.
Great, that was a really good and effective overview. I liked all the examples. Any questions for Brandon?
So I have a question, Brandon. So currently, is there a vault time set on the HPC? Like if somebody is running something for, say, more than 48 hours, are those jobs getting killed?
Not that I know of. I don't think so. We haven't had any issue with it. There might be a cap that's really high, but I've never seen anyone go past. I think the longest I've seen is maybe 2 days. But I think at that point, like eventually you hit the queue cap that you specified in the job script and the job just quits.
Okay, I just have a quick comment when you talked about your factorial example, how you can run this program faster on HPC. I perhaps may have a more striking example and experience by Dylan, who is working on an EPSCoR project. So running his program, some kind of transformer model on a regular computer would take hours, if not days. And then he moved it to HPC on a GPU, and he said, the program would run pretty much instantaneously. So yeah, you're absolutely right. It depends, the amount of speed up really depends on the particular example. So I just wanted to say that sometimes it's astonishing. So the example that you showed here, maybe HPC would double the speed, but with some examples it's just like many orders of magnitude faster.
No, yeah, you're absolutely right. This is a little bit of an underwhelming example, but I think for educational purposes was my main point. But yeah, you're absolutely right. There's a lot of cases where the HPC will speed it up tenfold easily.
Thanks.
Good. I like to build Alexander's comments, probably knows what I'm saying, because being part of the EPSCoR grant and the HPC planning grant that we had through the National Science Foundation through UNI. So I'm at Central College and I'm a chemist. And so my colleague here, when she runs her computational calculations on chemistry programs, generally the average calculation takes around a week. And so we were hoping when we were doing part of the planning grant to get access to the HPC at UNI, which you guys gave us. But the problem was there was no chemistry software installed. And so we can't run kind of what the standard protocols for the chemistry. And then you noted that chemistry bought some software. So of course, my curiosity is chemistry is what software did you buy? And then I'd be excited to use it to see if we can really kind of ramp up some student research projects with access to the HPC.
Yeah, we have, I forgot his name off the top of my head, but he purchased Gaussian, and that's what's running on it. And he also has a virtual machine that's running Gaussian View.
It's Gaussian. That's the standard. That's the standard in my field, right? Like,
yeah, that's what he said too. I think if you reach out to him, he might let you use the Gaussian View, but apparently, according to the license, he's only allowed to have it on one machine.
We have it here, and then that like they didn't have it at UNI. I was like, I'm sure someone at UNI has Gaussian, because it's just the standard, like using other. Sorry, my kids are off school and now they're just like.
I didn't hear anything, so you're good.
All like, I'm getting texts and calls. I'm sure they're fighting, but. All right, sorry to bother you with that, but yeah, Gaussian is that's like, so like that one piece of information now moved us from not being able to use the HPC to actually now we could actually jobs to like send you probably like this afternoon, right? Like if we won't, but I mean, I'm ready to go. We've code ready to, and we just need to learn through the tutorial that you gave us how to do it. So thank you for that tutorial. That was really helpful.
I was going to build off of Jay. So in your example, Brandon, you showed accesses through VPN and credentials from UNI. Can you explain to since Chemergy spans beyond UNI, how they would log in, or how, if that's a difficult process?
I think I should get out of the presentation mode. I have Cisco, and I'm not sure how you guys would apply, because I had to log in through my UNI account to apply to Cisco. But once you have Cisco installed, you can press connect, and then it asks you for your CAT ID credentials to log in on campus.
Maybe this is more for Alexander. I know before you sent out how some credential or access for this. Is this something, if Alex is still there, something that others can use?
Yeah, I'm not sure, Nigel, if I understand you completely, but yeah, just like one can get the actual HPC account at UNI, they can also get, especially for EPSCoR researchers, they can get VPN account. And then once you connect to UNI virtual private network, you can access HPC just like as if you were on campus. I don't know if this answers your question. Maybe you can repeat, but
yeah, no, that does. And maybe Jay is our guinea pig on this in terms of getting access, because maybe you can correct me, but I don't think anyone from Chemergy has yet accessed and used the HPC resources.
Yeah, I know we need to go. That should be and again, the tutorial is great because that looks like it should walk us through it, so we don't need that. And then I think Alexander somehow got us something with permission. Probably have it in my inbox somewhere to ask for the permission to access.
Yep.
Yeah, part of the problem, actually the problem is twofold. First of all, I think many people from chemistry, in particular, people who do some kind of computing, have similar resources. If not in their lab, they have those resources at the university. For instance, University of Iowa has large cluster, just like this one, but much larger. The second issue was really the manpower. But now we have Brandon, he's part-time, I believe, fully devoted to this. So, all these requests can go through him, and I'm sure, when it comes to technical issues, certainly all of those can be resolved.
Great.
So would that be reasonable then to just kind of restart and just ask Brandon what we need to submit to get, a username or whatever, and then go use that as a point of contact? I think we had a different.
Yeah, I can talk to our people at the IT department, because I have to reach out to them to get them in, to get it set up.
There's no urgency other than we couldn't do it before, and maybe now that you have been hired at UNI, like now we can.
Yeah. Like
again, last time Alexander and I talked, maybe like months ago, maybe we went from that to not quite a year ago. We went to we were something, but now that enough has changed that it might be enabling some of these things we want, and hopefully these will be really useful if the grant applications ever open up for more HPC grants to enable some of our ideas and get some funding for more infrastructure support.
I wrote your name down. I'll see what I can do about it.
Awesome. Okay, I was gonna say I'm going to send you an email, but yeah, I'm happy to be at least a guinea pig somewhat for the team, especially from what we might call under resourced institutions that need more collaboration and access to more.
I just wanted to add one thing. Actually, some EPSCO researchers or the whole labs applied for both accounts, for VPN account and HPC account. And we had, I don't know on the top of my head, maybe a dozen people from outside of UNI applied for accounts. Those accounts were given to them. I was actually personally involved in this, using FireLocker to give them credentials. But for some reason, I don't know whether it's a steep learning curve. It's not totally obvious how to connect, and Nigel is right. Not many of them, to my knowledge, have utilized HPC in those accounts.
Yeah, so it's good that we have you, Brandon. So yeah, we'll look to you to kind of help us bridge that to get the access, and then also as we run some.
Yeah, and I'm excited to hear that it's more than just our chemistry department that wants to use Gaussian on the HPC at least.
So what I can do, maybe, Brandon, I can forward you the names of people who expressed interest in the past of using UNI HPC, and then we can maybe get in touch with them to see whether we can help them once more to get connected and to use these resources.
Yeah, that'd be great, actually.
Yeah, I'll follow up with that.
Okay. So Brandon, at current kind of run capacity, do you feel the HPC is kind of always booked? Does it seem like there's still resources that could be used, or?
There's definitely resources that can still be used, because a lot of the time it's not being used. There's occasionally like hot moments where like the queue is pretty long, but I mean, right now I don't think anyone's running on it like at this exact moment. Right. So there's definitely resources that can still be used.
Okay, yeah, because to Alexander's point, our universities have these things and our labs do too, but sometimes they could be booked, so this would be a nice additional resource where it's like, oh, I need to run this, we could run it over there and get the results back.
Right, and of course the reason for this is that HPC is meant to be a one-time thing for running your software. Actually, it's not actually a good practice to connect it to any live service like web server that accept incoming data, and then those get sent to HPC. If this was the case, actually, you and I would alone keep this resource busy all the time. But yeah,
that makes sense. Okay, great. Any other questions for Brandon? Okay, if not, we're very appreciative of your time, Brandon, and it's been recorded so that way we can share it with those who weren't able to make it. But yeah, hopefully we can keep reaching out to you and using this in practice. So really appreciate your help.
No, I'm glad to be here.
Okay, great. Okay, thanks everyone. Have a good rest of your Friday.
Thank you. Stay warm. Bye-bye.
Yeah, indeed. See ya.
Yeah.
Team. So I don't have any other announcements or needs, but Brandon, time's yours, and we look forward to asking you some questions afterwards.
Okay, thank you. I appreciate it. Well, I'm Brandon Schmidt. I'm the HPC System Support Specialist at UNI, and I'm here today to talk to you about the HPC. So an overview of what I'd like to cover today. First, I heard some of you guys might not even be exactly familiar with what the HPC is, so I'll briefly go over what the HPC is and what it has to offer. And then we'll talk about how you can use the HPC and get the most out of the resources that we have available. And then next, we'll talk about how to access and actually use the HPC, because obviously you have to do it remotely. So it'll be something nice to walk through. And then we'll go over some of the things briefly that the HPC is being used for. And then I have a little demo that we can go through. So starting off, what is the HPC? The The HPC is a group of compute nodes that work together to solve problems that are too large or memory intensive for regular computers to handle. And you can see a photo of the HPC right here. Now, obviously the HPC is just a bunch of regular computers. They're high performance CPUs and large amounts of RAM, but all of these work together. We have a bunch of compute nodes and we have a head node and we have a node that you log into, and all these work together to solve problems. There's no user interface, so we have to connect remotely using command line. We can accept job requests and then put them into the queue, and that's how you submit and get things done. Job processing time isn't an issue because the HPC is running 24/7. This is an important thing because if you were running on your local machine, you'd be using all the resources that you have available and you can't do anything else until you're done. And that could take days or weeks using just a regular computer. So what are the advantages of the HPC? Memory intensive tasks become possible. Obviously on a regular desktop, you might be lucky to have 32 gigabytes of RAM. On the HPC, each node has 128. So if you need 60 gigabytes of data to be loaded in and worked with, then we're able to do that. You can run for long periods of time. I mean, most jobs on the HPC run for, I'd say like 8 hours, but sometimes they run even longer than a day. And on a desktop, that would take a serious amount of time. We have a large number of CPUs available for parallelization. We'll get a little bit more into parallelization because that kind of is the main way you want to use the HPC. It's not the only way, but it helps a lot, and that's what speeds up the process. Its advantage is simple. It just has more resources than a regular desktop. But the tricky part with using the HPC is trying to get all of the value out of these resources. Okay. So what the HPC isn't is it's not a black box that'll magically make things run faster. So if you have code and you're running it on your desktop, you can't just move that to the HPC and have it run much faster. You have to put some thought into making sure that you use all of the resources on the HPC and actually get value out of it. It's not a place to test and develop code. If you want to run a project on the HPC, it's easier to develop the code and then put it on the HPC, and you want to test it on your local machine. That's a lot easier because working